Okay, so we looked briefly at some few methods to change the logical effort of gates, and there were still static CMOS gates, sometimes special cases like skewed gates, etc. The next family is called as ratioed circuits, and we are going to look at one particular type of ratioed circuit. So before we go into this, just a little bit of history. The beginning of this unit, we said that three different logic families: static CMOS, um, pseudo NMOS, and dynamic CMOS. And pseudo NMOS is one particular example of ratioed logic. Dynamic CMOS is the next part of this unit. And one thing that we have to remember is still by far static CMOS is the most popular. Around, if you look at all digital circuits, around 95% of them are static CMOS cells from the standard cell libraries. If in some part, in somewhere in the critical path, we are not able to meet the timing requirement at all, and all possible options are depleted, then we will think of replacing the cells with some dynamic cells to increase the uh, delay, to reduce the delay. But other than that, there is no particular case where directly we will go for any other option except static CMOS. And ratioed circuit, as we will see, it's largely historic. With only one type of transistor, we are able to make the full circuit, and this was very popular when CMOS technology was not there. So when the first microprocessor, for example, Intel 4004 was made, it was only using NMOS technology. They did not have CMOS technology at that time. So then these families were popular, but now they are largely historic. They're not used in any of the circuits. So the two commonly used ones are static CMOS and dynamic CMOS. So, but for historic reasons, we will still look at ratioed circuit, and in particular, we look only at one type of family in that is the pseudo NMOS. And what is the meaning of this ratioed circuit? It's just that the output never goes to the perfect value, and it is a function of the W by L. And these are some example of ratioed circuit. The first one here, we have a resistor. So obviously this will always be conducting when the pull down network is conducting, and when the pull down network is not conducting, this is an open circuit. So that is the resistor's functionality. And the advantage is that it requires only NMOS transistors. The inputs are only given to NMOS transistors, they're not given to any other transistors. Disadvantage obviously is that resistor can be quite large to fabricate depending on the size, because now we need the output to go as low as 0 when this network is conducting, which means that if you look at the voltage divider across these two regions, we have to make sure that this is as close to 0 as possible, which means most of the voltage falls across this resistor and its value has to be quite large, because of which the area can be quite large also. And the second one, we can get rid of this resistor if I use an NMOS transistor. And if you remember from before, NMOS is generally not used in the pull-up network because it's not a good conductor of logic high. But we're doing something different to get rid of that problem. We are using a different power supply, VGG. And the value of this power supply should be such that this conducts all the way up to VDD. So there's two separate power supplies. It cannot be the same as this. Then we will have the problem that this NMOS will switch off when this node reaches VDD minus VT. So we have to have a different power supply that allows this to go all the way up to VDD. And that's a problem because when you have multiple power supplies, you have more noise uh, between those power lines, etc. So that is the disadvantage of this second circuit. The third circuit avoids both of these issues by having a new type of transistor. This is a NMOS depletion type transistor. So this darkened line means that the channel is fabricated, which means that this transistor is always on. and we have to apply a negative voltage to turn it off. This is a good option, but only thing is it requires extra uh, steps for the fabrication, which makes this transistor a little more expensive. So all this is the evolution of ratioed circuit until we can come to the family that we are talking about, which is called as the pseudo NMOS. So in pseudo NMOS, instead of the three options that we saw there, the resistor or the NMOS load or the depletion NMOS, we put a PMOS transistor, and the PMOS transistor is connected such that it is always on. Okay, and that is going to be the pull-up network, and this is going to be always on. Okay, so let's just quickly look at the circuit and see if I can zoom in a little bit here. So this is the circuit. This is what it looks like. There is a PMOS transistor, and irrespective of the pull down network, the pull up network is only one PMOS transistor. And pull down network can be anything. This is where we realize the functionality of the gate, and output is as always in the middle. And there's a little bit of a problem. Pull down network is conducting, pull up network is always on conducting. So when the pull down network is not conducting, then the output is at a very good value, which is logic high or VDD, because there is no current flowing. But when the pull down network is conducting, pull up network is also conducting. So now it is the case of a voltage divider circuit. That is, the pull down network will have some voltage across itself, pull up network will have some voltage across itself, and based on the voltage divider ratio, based on the resistances of both the networks, V out will be at some value between 0 and VDD. So as the designer, we have to make sure that when the pull down network is conducting, okay, V out is as close to 0 as possible. That is probably why you see this very large value of 16 for the transistor. And how do we design that value? Before we go into that, there are some rules. Let us look at these curves. These curves are very useful to understand. If you remember the ideal value, okay, for the VTC of an inverter, this is close to the ideal value. It starts coming down like this, but the ideal value for a static CMOS inverter, it will reach 0. So at these ranges, this curve will be here. But since we have a large value, since we have a PMOS transistor which is always on, okay, this curve can never reach this particular value, and it is going to be at different levels depending on the size of the transistor. And that is what we see here. What are these multiple curves? They are drawn for different values of PMOS size, single PMOS transistor. So the same curve, PMOS, this is the value of the size for P equal to 4. Okay, so if the PMOS is 4 and the NMOS is 16, the curve is not too bad. It's not ideal, but it's close to ideal. VDD, when the input is low, output is at the perfect value. When the input is high, which is 1.8 volts, output is not at the perfect value, but it's pretty close. So maybe around 1.05 volts or something, which is very good, as close to 0 as possible. So that can be achieved only when we put P equal to 4. If you use your normal logic, if the PMOS is NMOS is 16 and the PMOS is 32, that will be worse than this also, which means that it will be somewhere here. When the input is high, output will be around 0.75 volts, which will be not a workable value. So we have to do something as the designer to make sure that we get this type of curve for every gate. Okay, we cannot work with these curves. So how did we decide on P equal to 4? That is the next thing that we have to see. How did we decide to put p equal to 4 and get this curve? And the way we do that, we have to do a few things for that. To look at the sizing for the PMOS transistor, there are two things that two rules we have to use for the sizing. The first rule is that the PMOS network is half. Okay, now this is the exact opposite of the sizing rule from before. Before, for the unskewed cases, the PMOS network was twice the size of the NMOS network. Now what we are saying is the PMOS network has to be half the size of the equivalent NMOS network. And since we know that size is inversely proportional to resistance, if we make it half the size, then it will have how many times resistance? Not 2 times, because PMOS per unit is already 2R. It will have approximately 4 times the resistance of the pull down network, and that is the equivalent voltage divider circuit that we want. Okay, so that is one condition. Another condition is the current. Okay, so there is a current flowing. How do we make sure that the gate is fast enough? Okay, the problem with the discharging network is when the network is discharging, okay, PMOS is still on and the PMOS is continuously charging the network. So the NMOS network is trying to discharge the output node, PMOS network is continuously charging the output node, so that is not a good situation. How do we make sure that the gate is still fast enough? For that, we have one more equation, which is the average discharging current should be the same as the unskewed inverter discharging current, which is nothing but VDD by R. If you look at any unskewed inverter, the pull-up network or the pull-down network, their equivalent resistance is R. And if you average the voltage across the terminals for the charging or the discharging, it's VDD by R. So that is the second condition, and we have to use both these conditions simultaneously to get the size for the pseudo NMOS network. So let me just repeat this again. It's not as complicated as it sounds. When we do the examples, we will see, but there are two conditions. Okay, the first condition to put the sizes, we have to size the PMOS transistor half the size of the equivalent NMOS network, not the NMOS transistors. Okay, NMOS can be multiple transistors, but the overall NMOS network will have some W by L. The size of the single PMOS transistor should be half of that size. Okay, that is the first condition. And the second condition is in terms of the current flowing during the discharge. Whatever current, the average current flowing, that is the NMOS current, is flowing downwards from the output to the ground. The PMOS current is flowing from the VDD power supply to the output node. So the difference of those two currents, that is the average current discharging, should be the same as a inverter, static CMOS inverter, which is VDD by R. So together, if we use these two conditions, then we can come up with the sizes that satisfy our pseudo NMOS gate in terms of both speed and in terms of the proper values for the output voltage. So let us not worry about this now. Let's look at sizing. Okay, so let's go back to the inverter itself. Let's draw the inverter and try to come up with the sizes for a pseudo NMOS inverter. So we'll draw the inverter. Okay, inverter is relatively simple. Okay, don't give the input to the PMOS also. Input comes only to the NMOS transistor. PMOS is grounded. So this is the output. Now the first rule to follow is we want to give sizes. So let's call this K. If this is K, our rule says that this should be K by 2. Okay, we don't know what is the value, so we'll just put it as K and K by 2. And now we will try to use the second condition in terms of the current to find out what is the value of this K and K by 2. So we have the difference of two currents. Okay, the one is the current flowing through the NMOS transistor, other is the current flowing through the PMOS transistor. So first we will write the NMOS transistor current. NMOS transistor current, we'll just use average value V by R, V VDD divided by what is the resistance of this single transistor. Its resistance is R by K. Okay, minus VDD by what is the resistance of the PMOS transistor. Why do we have a minus? Because the current direction is different. NMOS transistor is like this, PMOS transistor current is like this. So the net current discharging the output node is this minus this. So that is this minus VDD by 2R by K by 2. Okay, this is the current flowing through the PMOS transistor, and this should be equal to VDD by R. That is what our condition is telling us. We want it to be equal to VDD by R. So this is the equation. In this equation, if you solve this equation, we can solve this equation. There's only one variable, that is K. VDD gets cancelled all over, R gets cancelled all over. We can solve for the K. So you should get something like K minus K by 4 equal to 1. No, maybe that's wrong. Let's just solve for K offline and bring it back. Maybe that analysis was correct. So K I got is 4 by 3, which means the NMOS is 4 by 3 and the PMOS will be K by 2 is 2 by 3, and this satisfies all the conditions that we require in terms of both the speed and the proper values for the output. Now the next thing is we can calculate the logical effort also. So similar to before, we have GU and GD. So we will calculate from here GU, we'll calculate GD. Okay, so just like before, you size the network with a unskewed static CMOS inverter, and the size should be according to the pull down network. So that is what we have to do. So this is 4 by 3. Okay, and this is 4 by 3 means this will become 8 by 3. And this is 4 by 3, this is 8 by 3. So GD equal to input capacitance of my gate. So it is just 4 by 3 divided by 4 by 3 plus 8 by 3. That is 12 by 3, rather 4, not 3. Sorry. Okay. So in the logical effort, I just made a small mistake. This is a little bit of a problem because we can't directly put 4 by 3. Actually, our life is much simpler for logical effort calculation because by default we sized it similar to static CMOS inverters. So that means that this is 1 and 2. And why we can't put 4 by 3 is because even when this 4 by 3 is working, this is also trying to charge the node. So the effective W by L is 1, not 4 by 3, which means that this becomes 4 by 3 by 3, and that is 4 by 9. Okay, so that is something that is relatively easy to calculate for all pseudo NMOS gates. When you're doing the calculation for GD, always your equivalent inverter is 2 and 1 because that is what we used to get in this equation. So by default, the equivalent inverter size is going to be 2 and 1 irrespective of the pull down network size. So whatever you have for the input capacitance, you just have to divide that by 3 and you will get the logical effort for the pull down network. Okay. And generally GU we don't care because that is happening through this network which is always on. So we calculate only GD. Okay. So let us try this for another gate. Let's take a 2-input gate, say 2-input NOR gate. So pseudo NMOS, remember the pull down network is just one single PMOS, only the pull down network has to change. Okay, so this is grounded, this is the output node, and we have two transistors in parallel. Okay, now we have the gate sizes. Okay, let's just say this is K and this is also K. Okay, and in the worst case only one is conducting, and that will make this as K by 2. Okay, and this is the equation. And if you write the next part, which is the current equation, okay, you will get approximately the same value for K equal to 4 by 3, and that means that PMOS equal to 2 by 3, and everything else stays the same. Logical effort also you can calculate in the same way. 4 by 3 divided by 2 and 1 is you will get 4 by 9. So interesting outcome in a 2-input NAND gate. It is the same as an inverter, which is 4 by 9. So you can try to do this for a 2-input NOR. We did this for a 2-input NOR gate. You can try to do this for a 2-input NAND gate. See if you're getting these sizes: 8 by 3, 8 by 3, and 2 by 3. Okay, so this is our pseudo NMOS logic family, and we looked at some examples for sizing, etc., and we saw this example also: 4 by 3, 4 by 3, 2 by 3, and it says GD calculation here. So GU we saw, we saw GD calculation. It's very simple. Whatever is this thing, the pull down network is going to be equivalent to a 2-1 inverter. So the equivalent inverter is also is going to be 2-1. When you're doing the GU calculation, this is 2 by 3, which means that becomes the, so let's just do it maybe for this example, the equivalent inverter, okay, for this particular transition is going to be, this is my static CMOS unskewed inverter, and the PMOS size is 2 by 3. So the NMOS size is going to be half of this. So easily I can get 1 by 3. So therefore GU equal to, now little careful, input capacitance of my gate. So don't look at this, this is not part of the input. Okay, what is the input capacitance of this gate? We got K is 4 by 3, right? So if you want, I'll write that here, 4 by 3. So the input capacitance of my gate is 4 by 3, and input capacitance of my gate to input capacitance of equivalent static CMOS inverter for that transition. So GU is going to be 4 by 3. Okay, this is how we calculate GU. Size the network based on the size of the PMOS transistor, and MOS is double that. Then input capacitance of the gate, look at the pull down network, don't look at this one. This is not an input, right? This is permanently grounded. This is your input capacitance divided by equivalent inverter is 2 by 3 plus 1 by 3 is 4 by 3. So this is the value for G. and this is the method you can follow for this example also. Okay, so we will skip this. We'll continue in the next class with dynamic circuits.